Okay, so as I mentioned, the second important equation, we call that the Euler's equations, is quite important in our class. So now, right now, our purpose is how can we prove the final Euler's equation formula, just showing right down, right corner in here. Okay, so this is our purpose. So we start from the force balance. The first is we know that along the L directions, the straight line directions, so the sum of the FL that indicate all of the force along the L directions not equal to 0, right? In the previous, for the hydrostatic equation, we consider sum of the force along the L directions equal 0. But right now, we don't have this condition because we call that the particle is accelerating right now. So we have the mass and we're equal to the accelerations along the L direction, right? So we have the acceleration and along the L directions. Okay, so we need to have the two parts. The first part, how about the sum of the force along the L directions? So as we know, the first force contributions from the pressures. So we have the pressure force, and I use the FP. It indicates the force from the pressures. And the second force will from the particle weight. So I use the force, FW indicates the force along the L directions contributed by the weight, the particle weight. So what's the FP? So we know that we have the two items. The first one is the P delta A on the left-hand side, and right-hand side we have a P plus the delta P multiply the delta A. Okay, so we know that the force pressures on the left-hand side is the positive because the direction is go to the right. So we have the P delta A, and the right-hand side, the pressure force is the negative, go to the left. So we have the minus, the P, delta P change it, and multiply the delta A. The delta A is the area of the particle surface. Okay, this is a delta A. Okay, so you can rearrange the pressure force, and you know that some item cancel out already. So we only have the minus delta P multiply delta A. And the P multiply delta A already cancel out each other. Okay, so this is the force related to the pressure. So the second, we have the FW is the particle weight project along the L directions. Okay, so actually the particle weight is delta W. As you can see, the delta W along these directions. So we have the L delta W downward, but we need to project to along the L directions. So delta W project to the L directions. We have the sine alpha angle in here, and we'll project to along the L direction is these directions. Okay, and we know that the sine alpha based on the summarized figure in here. So the sine alpha in here, we know that the sine alpha will indicate equal to the delta L over delta Z, right? So you can take the place, replace the sine alpha by the delta L over delta Z. And because the directions for the weight is negative directions, so we have additional minus in here. Okay, So finally, we know that the minus delta W and we have the delta Z divided the delta L, right? Because we replace the sine alpha by the delta L over delta Z. And we also know that the weight. How can we compute the weight? If we know the particle gamma, because we have the gamma, and gamma multiply the delta V. Delta V is the volumes of the particle. And then we can compute the delta W. Okay? So we can rewrite the equation like this formula. And we also know that the delta V can be rewrite by the delta L multiply the delta A. Okay, what is delta L? Delta L is the total length of the particle. Okay, so we just have the formula in here. So some item you can cancel out the delta L, and finally you know that the FW is minus gamma delta A multiply delta Z, right? Okay, so it is our final items for the FW. So we go back to see our equations in here. So we can rewrite the equations to be the FP is the minus delta P. Minus delta P divided multiply delta A. This is FP plus FW is minus gamma delta A delta Z. It will equal to the mass multiply the acceleration along the L direction, right? And we know that the mass, the particle mass will equal to the density, okay? The density multiply the volumes. And we already know the volume is the delta L multiply delta A. And we keep the acceleration L in here. Okay, so right now you can cancel out some parameters you don't need. So the first one is delta A, and delta A. Okay, so and I just reorganized the equation to be the delta P minus the gamma delta Z. Okay, and the density delta L and the A acceleration along the L directions. Okay, so the formula showing here right now is much close to the final item we need. So only one difference is the delta L on the right hand side. The delta L on the right hand side. So we divided the delta L both sides. So we can rewrite the equation to be the minus delta P divided the delta L minus gamma delta Z divided the delta L, and will equal to the density multiply the acceleration A. But still difference, right? Compared to our final formulas. So I just pick out the one important item. We just look for these items. Okay? So if I assume the delta L and the delta L is quite smaller, and I can change the delta L to be the dL, right? The differential operators. So all of the equation I write down in here, I can change to the minus delta P divided the delta L minus the gamma dz dL, and equal to the density multiply AL. But as I mentioned, I take a look for these items. Why? So I just write down one equation to you. So it is if I compute the differential differential L, okay? But the inside item to be the gamma and the Z. So I do the partial differential for the gamma and the Z. The differential answer will to be the gamma dL multiply the Z plus the gamma dZ dL, right? And as we remember the one assumptions for these questions, when you derive the equations, the most important is we assume the flow is incompressible flow. If the incompressible flow, the density is always constant. The density constant, that indicates the gamma also constant. So the gamma in here didn't change with the L difference, right? So this item will always equal to 0. So we know that the final, the dL, the gamma Z will equal to the gamma dZ dL, right? So we replace the items, we replace this item, the square I highlight in here will to be the dL, and the inside is the gamma Z. Okay? So we can rewrite the final formulas. Okay? So just based on this final equation, and we rewrite the equations to here. Okay, and use the red color. So the minus dP dL minus the dL, but the inside is the gamma Z, and will equal to the log AL. And we still can merge the items, so the minus put outside, and the dL, the inside is the P pressures plus the gamma Z. Okay, and the final equal to the log AL. And the pressures plus the gamma Z is the piezometric pressures. And the gradient operator in here is the dL. So the L is along the straight line directions. So the piezometric pressures along the straight line directions gradients minus will equal to the density multiplied the accelerations. And these accelerations also with the directions along the L directions. Okay, so the piezometric along the straight line gradient minus will equal to the density multiply the acceleration along the straight line. Okay, this is Euler's equation. OK， 所以尤拉方程的意思就是说，在沿着流线方向上或是路径方向上的侧压压力变化取负号，就会等于流体密度乘上它在流线方向上的加速度。OK， 那这个就是我们说的 Euler's equation。OK， I think maybe some part you cannot fully understand, but I write down all of the scheme when how can we derive the Euler's equation. So when you go back to home and you can check from the video and to see some details. But the most important two assumptions we need to remember if we would like to apply Euler's equation. The one is inviscid flow, so no viscosity effect. The second is incompressible flow, so the density is constant always. Okay, only two assumptions we need to remember when we apply the Euler's equation. Okay, so some idea, the physical interpretation for the Euler's equations. So the first I already know, teach you the case one. is a pressure variance due to the changing speed of the particle. Okay, and some idea, as you can see, there is a string line, there is a string line, and all of the string line parallel each others. But if you plot one vertical line, is a normal, the line normal to the string line, and the piezometric pressure along the normal, the string line normal, the line normal to the string line, the blue line in here, all of the piezometric pressure along this line, the blue line, are the same. So along the blue line, there is no accelerations in that directions. So let's here tell you the pressure variance normal to the linear string line. Sometimes we don't have the pressure variance along the normal to the string line. Okay, so there are some the sentence have more detailed interpretations, and you can look by yourself. And the case 3, but if your curvature is, your string line is the curvature line, so if I plot one normal, the line normal to the string line, in the case 3, there is the pressure variance, because along the normal direction we have the accelerations. That indicates along the blue line there is the piezometric pressure difference along the string line, and then we have because the piezometric gradient is not equal 0, so along the normal direction we have the accelerations. Okay, so that is some basic knowledge for the Euler's equations. So right now we can have the couples exercise, and we know that the reason why. Okay, so this is the first questions we can practice. How can we apply the Euler's equation? So we have the vertical tube, and the inside we have the water column, and I tell you we accelerate by a piston in the vertical directions with the accelerations 100 meters per second square. Okay, so we have the AZ acceleration put outside upward, and the depth of the water column is 10 centimeters. Please find the gauge pressures on the piston. Okay, so that's the questions we need to know the point in here, how large gauge pressure we have. How large gauge pressure we have at this point. Okay, so we would like to calculate the point in here, and we have some reference point. Maybe I use this is the P1 and this is the P2. So we need to know how large the P2 we have. Okay, so we know that in that case the water density is the 1000. Okay, so we assume some assumptions. The acceleration is constant. Okay, very important. And the viscosity effect we no need to consider. And the water is incompressible. So all of the assumptions shown here are satisfied for the Euler's equation. So we can apply the Euler equation very quickly. Okay, so the idea is maybe we have the directions along the Z. Upward is the positive. Upward is the positive. Okay, so we have the based on the Euler equation, we know that the gradient, piezometric gradient along the Z directions, because right now our straight line is along the Z directions. And the piezometric pressure is equal to the P plus gamma Z, right? And we're equal to, and very important, we have the minus in here. We're equal to the density multiplied the accelerations along the straight line. So we have the AZ as the acceleration, right? the AZ. So how can we solve the problem? Because what we need the P, okay? The answer we need to provide to the P2 pressures. Okay, so right now we just combine all of the parameters together. So we have the differential, the P plus the gamma Z, and I move the dz to the right hand side, and I can do the integrations both sides. So I can do the integrations for the both sides, and I know maybe my condition is I start from the point the Z2 to the Z1. So the Z2 go to the Z1, and the Z2 is the elevation in here, and this is the Z1. Okay, and how the point I start from the point 2 going to the point 1. This point 2 to the point 1, the piezometric difference is equal to the right hand side, the integration along the Z directions. So we know that the here is will equal to the minus the P1 plus the gamma Z1, and the minus will be positive to the P2 plus the gamma Z2. And the right hand side, what do we have? We have a constant value of the rho and the AZ, and the Z is from the Z1 minus the Z2, right? Okay, we just do the integrations. So I can remind you the P1 is pulse on the atmosphere. So the gauge pressure at the P1 always equal to 0, right? So we don't have the P1 values. So we reorganize the equation. So in here, the minus the gamma Z1 plus the P2 and the plus the gamma Z2 will equal to the rho AZ and the D1 minus D2. And I keep the P2 on the left hand side and move all of the parameter to the right hand side. So it will equal to the rho AZ D1 minus D2, and the plus the gamma, and it's equal to D1 minus D2, okay? And we know that the gamma is equal to a rho G, right? The gamma is equal to a rho G. So we have the same parameter is rho, and the inside is the AZ plus the G, and we have the Z1 minus the Z2. Okay, so this is our final formula for how can we compute the pressure at location 2. Okay, so what the A, if you take a look at the G, okay, the G, when we only consider the hydrostatic equation, so the G is, if we only consider the gravity, the answer will be the hydrostatic pressure, right? But right now we have additional velocity, additional accelerations contribute from the piston. So the pressure will increase compared to the hydrostatic conditions. Okay, so we can put all of the answer in the number inside. We have the 1,000 kilograms per meter cubic, and the acceleration is the 100 plus the 9.81, and the unit is meter per second square, and the Z1 minus the Z2 is equal to 10 centimeters. So we convert to the meter is 0.0 0.1 meter. Okay, so finally you can compute the final answers for these questions. Okay, because the number is quite simple, so yeah, it's equal to the 10.9 kilopascal. And right now we compute the pressure is the gauge pressures. Okay, so this is one simple questions. If we already know the accelerations on our flow, and we can compute anywhere the pressure how large it is. OK， 那这个是很传统的这个练习，就是说，因为我们的流场是被加速的，所以你不可以再用单纯的流体静力的概念去思考这个问题。以前我们流体静力的概念，如果要算 P2 这个压力，是不是很简单？伽马乘上水的高度，就是在 P2 的压力。可是现在不能这样子，因为有一个东西在加速，所以它会提供额外的压力。那所以我们的压力会变大，对不对？不会像镜子在那边一样大。Okay, so the idea is today most important is we just try to compare the hydrostatic equation, the result, compared to right now the Euler's equations, the difference. Okay, because our fluid particles start to accelerating. So the condition is not related to the static condition. Okay, so we may practice the second exercise. So the second exercise, again, we need to apply the Euler's equation again. So you see our questions, we have the tank, and we fill the gasoline inside. It's a field complete. That indicates all of the material inside are the gasoline. Okay, just fill all of the gasoline in the car. And we know that the specific gamma and the exercise provides 2 units. So I only focus on the unit for the SI unit. And for you can decide which unit you want. Okay, so we know that the gamma for these questions is the 6.6 kilo newtons per meter cubic. Okay, it is the gasoline specific gamma, specific weight, and the truck is decelerating. The decelerating indicates the car move from direction. We have the opposite, the accelerating. So the acceleration is to the back, and we have the acceleration to the back. Okay, and this is acceleration is equal to the 3.05 meter second square. So right now we have 2 questions. The one question is the pressures at the top in the end of the tank is the atmosphere. Okay, that indicates the pressure in here. The pressure in here, maybe this is my P1 point is equal to 0. The gauge pressure is 0 because this point that we assume is posed on the atmosphere. And what the pressure at the top from? So what the pressure at the top from is in here. So the P2 in here, the top from. So the first question is we need to answer how large magnitudes of the P2. Okay, and the second question is what is the maximum pressure in the tank? So we consider all of the pressure on the top. So that indicates on the bottom point, the pressure should be increased, right? Because on the bottom, the point on the bottom, we still need to overcome the gasoline liquid weight above the bottom, right? So I directly tell you the maximum pressure in the tank will be on the right corner. and I mark with the P3. So this is we need to calculate the P3 magnitude. Okay, so go back to see some background conditions. So we know that the acceleration is constant and the gasoline is incompressible. Okay, so we double check. So the questions also satisfy the Euler's equation assumptions. Okay, so the directions for our problem along the direction on the right hand side is the arrow positive directions. Okay, to the right. So we just consider the line in here. We consider the line in here start from the P1 to the P2. And the P1 to the P2 satisfy the Euler's equations. So again, we can write down the Euler's equation is the piezometric pressure. So dP gamma Z. And then right now the direction is the arrow directions. And the minus gradient will equal to the density. Okay, the density. And multiply the accelerations, arrow directions. Okay, acceleration with the arrow directions. Okay, because we need the density, so we have the gamma, so we can compute the density is equal to the gamma divided the gravity, right? So we can use the calculator to compute how the density we have divided the G. So the density is around the 672.78. So the density unit is a kilogram per meter cubic. Okay. So again, we do the integration problems. So we have what we have. We have the maybe the minus, and the inside is the P plus gamma, and we start from the 0.1 to the 0.2. Will equal to the low AL is a constant, and the L1 to the L2, and the inside is the DL, right? The DL, right? Okay, so again, this is a minus, and we have the P2 plus the gamma 2, the gamma and the D2, and this is a minus, and the minus to be the plus the P1 plus the gamma Z1. Okay, will equal to the low AL, and this is the L2 minus the L1, L2 minus the L1. Okay, so you actually know the L2 minus L1 because there is a number shown here. It's a 20 FT. Okay, this is a L2 minus L1. But later we just put the number inside. So right now we just consider some parameter can neglect. The first one is the P1 exposed on air. So the gauge pressure equal to 0. And our purpose is P2. So in that case, the minus the P2 and the minus the gamma Z2 and the plus the gamma Z1 will equal to the low AL, L2 minus L1. And in here, we know that actually the Z1 and the Z2 located at the same elevation. So that should be also just cancel, right? No need. So we don't have the item from the D1, the D2. And so we know that finally we have the minus the P2 will equal to the low AL and the L2 minus L1. So based on the formula showing here, so we can compute the P2 answer. So I just write down in here the minus the P2. We don't know the answer, right? But we know that the density is 672.78. and this is kilograms per meter cubic. And what are the AL in here? The AL we actually know is the 3.05 meter square second square, but the A acceleration direction is the opposite directions, is a negative. So in here, the acceleration, we have the additional minus in here, right? Because the direction is go to the left. The acceleration direction is go to the left. And multiply the L2 minus L1 is equal to the 20 ft. And we know that the 1 ft is equal to the 0.3048 meter. So we need to convert the ft unit to the meter. So the unit in here is the meter. So you can balance the all of the sign both two sides and compute the number. So I check the answer by myself, and you can try by yourself. Yeah, so the answer is, the true answer is the 12508 and the 0.9, and this is the par. Okay, so it's around to the 12.51 kilo par. So this is the P2. What do we have the P2? Okay, so we finished the question 1. We provided the answers. And what is the question 2 and why the reason I tell you the maximum pressure will happen at the P.3 in here. And just like the idea is we, based on the hydrostatic ideas, we just compare the P2 and the P3. And the additional pressure contribute from the P3. At the P3 is the gasoline high above the P.3. Okay? So based on the hydrostatic equation, I know the P3 will equal to the P2. Additional pressure is V plus the gasoline gamma, but with the high is above the 0.3. The gasoline high is the 6. It's the 6 ft, and multiply the 0.3048, and so the unit in here is the meter. Okay, so I put all of the number inside the equations. We have the 12.51 kilopar plus the gamma is the 6.6 1,000 Newton divided the meter cubic, and the later is the 6 multiplied 0.3048 meters, and you can compute the final answers. Okay, so I check from my calculators. 6.6 multiply 1,000 and multiply 6 multiply 0.3048. Okay, so the number answers is 24,578.9, the par. Okay, so it's quite close, equal to the 24.6 kilopar. Okay, so it is our second question's answers. What do we have? Okay, so the idea is even though in this chapter we start to discuss with the kinematic problem with the fluid, but we still need to apply the hydrostatic equation what we learned in previous chapters. Okay, so different conditions we need to apply the different equations. 那这个就是很传统的这个现实的问题，就是说 一台卡车，如果你没办法去计算它承载的一些重量在一个 tank 里面，万一它的强度，卡车如果它的强度没办法克服的话，那你东西载一载以后，原本好好的停在那没事嘛，可是你开车了，那你就有加速度，那有加速度它就会贡献额外的压力，即便是一开始你没有动，有一个压力嘛，那你移动了以后会有额外的压力。如果你设计不良的话，那它车开了就破康了嘛，因为一开就有多的压力，底座就破掉，然后所有东西就露出来。所以我们必须去设计卡车它装载的这个槽，它的底座的强度能不能支撑这样的压力。那你可能放在那里没事嘛，你就好棒棒鼓掌，然后欢迎它开出去这样子。就它一开一刹车，砰就全部都爆出来。所以这是很现实的问题，跟我们上一节课看那个影片，怎么那座桥在那边摇来摇去，大家感觉好像都很无所谓，可是那就是工程师设计有问题。大概是这样。好，那我今天想说，就不要再，今天大家都很辛苦，我今天可能停在这里好了，好不好？那我们就来